Welcome to G Fun Facts Online. Today we are uncovering a phenomenon that is fundamentally rewriting the chemistry of our planet's oceans, an invisible crisis occurring right beneath the waves of our most productive coastlines. We are talking about upwelling acidification. If you stand on the rugged cliffs of the Pacific Northwest or the arid coastlines of northern Chile, you see a picture of vitality. Seabirds diving, fishing boats hauling in massive catches. These regions, known as eastern boundary upwelling systems, cover less than 3% of the ocean's surface, but provide over 20% of the global fish catch. They are the ocean's breadbaskets. But hidden within this abundance is a chemical assassin. The same vertical currents that bring nutrients up from the deep to feed the plankton are also carrying a toxic payload of ancient, corrosive water. This is not a future projection. It is happening now, dissolving oyster larvae in Oregon and pitting concrete pilings in industrial harbors. To understand this, we have to start with Oceanography 101. Why do these specific coastlines have this problem? It starts with the wind and the rotation of the Earth. In places like California, Peru, and South Africa, winds blow parallel to the coastline toward the equator. As this wind drags across the surface, the Earth's rotation creates a force known as the Coriolis effect. This deflects the water movement 90 degrees away from the coast. This is called Ekman transport. As the surface water is peeled away from the shore, nature creates a vacuum, and cold water from the deep rises to replace it. This is upwelling. The water rising from depths of 100 to 300 meters is ancient. It has been out of contact with the atmosphere for decades, traveling slowly along the ocean floor. As it traveled, it collected the detritus of the marine world, dead plankton, and decaying organic matter. As bacteria break this down, they release carbon dioxide. Because this water is trapped deep down, that carbon dioxide accumulates. This makes the deep water naturally nutrient-rich but also naturally acidic. In a balanced world, this is fine. But we no longer live in a balanced world. We are now experiencing a double whammy. When this naturally acidic deep water hits the surface, it mixes with surface water that has absorbed massive amounts of human-made carbon dioxide from the atmosphere. The result is a non-linear amplification of acidity. It is a corrosive soup that creates a chemical flash flood. Let's look at the chemistry. Ocean acidification is often simplified as the pH dropping, but the real killer is the saturation state of calcium carbonate, specifically a mineral called aragonite. Marine organisms like oysters, clams, and corals use carbonate ions as bricks to build their shells. When carbon dioxide increases, it consumes these carbonate ions. Scientists measure this using the omega value. When omega is greater than 1, shells are stable. When it is less than 1, the water becomes corrosive, and shells begin to dissolve. The water upwelling today off the Pacific Northwest hasn't touched the atmosphere for 30 to 50 years. It is naturally sitting at a pH of around 7.6, much lower than the surface average of 8.1. When you add anthropogenic carbon to that mix, the safety buffer vanishes. The most famous case study of this happened in 2007 at the Whiskey Creek Shellfish Hatchery in Oregon. This hatchery supplies oyster larvae to growers from Mexico to Canada. Suddenly, billions of larvae started dying. The tanks would be full of swimming larvae one day, and the next the bottom would be covered in microscopic death. Initially, operators suspected bacteria, but nothing worked. They eventually brought in biogeochemist Burke Hales, who found the smoking gun. It wasn't bacteria, it was the water. When strong upwelling events occurred, the saturation state of the water dropped below 1. The water was literally dissolving the shells of the baby oysters as they tried to build them. The larvae were running out of energy trying to build their shells in corrosive water and dying of exhaustion. This was a wake-up call that ocean acidification wasn't a problem. For the year 2100, it was killing industry right now. The hatchery had to adapt by becoming a chemistry lab, injecting sodium carbonate to artificially buffer the water. But you can't buffer the entire ocean. This is happening globally. In the Humboldt Current off Chile and Peru, scallop larvae are being stunted. In the Benguela Current off Africa, the problem is compounded by hydrogen sulfide eruptions from the seabed, creating dead zones where rock lobsters physically walk out of the ocean onto the beach to escape the suffocating water. This brings us to the biological cost. It is not just about shells dissolving, it is about energy. Fish, for example, don't have shells, but they must maintain their blood pH. In high carbon dioxide water, fish have to actively pump ions across their gills to prevent acidosis. This burns energy. Juvenile rockfish in California have been found to be sluggish and slower to escape predators because they are metabolically taxed. Even worse, high carbon dioxide interferes with neurotransmitters in fish brains. Studies show that some fish lose their fear of predators in acidic water, sometimes even becoming attracted to the smell of their enemies. Recent research from 2023 and 2024 has uncovered an even more terrifying layer: the bioavailability of iron. Phytoplankton need iron to grow. New studies show that as pH drops, iron binds more tightly to organic molecules, making it harder for plankton to absorb. This means that even if upwelling brings up nutrients, the plankton might starve because they can't access the iron, potentially collapsing the food web from the bottom up. And it is not just biology, it is infrastructure. Concrete is highly alkaline. When it sits in acidic seawater, the chemical attack accelerates. The calcium is leached out, the concrete becomes porous, and salt water reaches the steel reinforcement inside, causing it to rust and crack the structure. Port authorities are seeing accelerated degradation of pilings and seawalls. So, is it getting worse? Unfortunately, yes. This is known as the Bakun hypothesis. As greenhouse gases warm the land faster than the ocean, the pressure gradient that drives the winds intensifies. Stronger winds mean stronger upwelling. We are spinning the spoon in the coffee cup faster. This brings up more acidic deep water, which is then mixing with even more polluted surface water. Models project that by 2050, large swaths of the California current will be permanently corrosive. However, there is hope in adaptation. We are seeing the rise of high-tech hatcheries using real-time sensors to dodge bad water. We are seeing the potential of kelp and seagrass meadows to act as phytoremediation, absorbing carbon and creating halos of safer water for shellfish. Scientists are also breeding super oysters that are genetically more resistant to acidity. But the ultimate lesson here is that the ocean is not a limitless sink for our waste. The corrosion of the coastline is a warning. The separation between the smokestack and the deep sea is an illusion. What goes up must come down, and eventually it wells back up to meet us. We are on a vertical front line, and adapting to this new chemistry is the challenge of our century. Thanks for listening to G Fun Facts Online.